हेलो एवरीवन, दिस इज निहाल एंड आज हम 2019 का यूपीएससी मैथमेटिक्स ऑप्शनल पेपर 2 का फर्स्ट ए क्वेश्चन जो कि ग्रुप थ्योरी का है वो सॉल्व करेंगे। क्वेश्चन कह रहा है कि लेट जी बी ए फाइनाइट ग्रुप एच एंड के बी सबग्रुप्स ऑफ जी such that k is a subset of h so that or k is a subgroup of h so that index of k in z is equal to index of h in Z, that is into index of k in h. This we need to prove. First of all, we need to know that what does that mean? Index of k in Z. It means number of distinct left or right cosets of k in Z. Let us assume that number of distinct left cosets of k in Z be R. That means G k is equal to R. This we have assumed. Now, since we have assumed that the number of distinct left cosets of G in K is R, and we also will हम एक result use करेंगे, result R1, that G can be written as union of distinct left cosets I is equal to 1 to R of K in Z. Or if the subgroup is H, then G can be written as union of distinct left cosets of H, where I from 1 to R1. So this is how G can be written. We later in the video we will prove this thing, that G can be written as a union of distinct left cosets. Now, what is the order of AIK is equal to order of, or cardinality, not order but cardinality. Cardinality of AIK is equal to cardinality of AJK is equal to cardinality of K. This is result 2. We will also prove in the video, at the end of the video, that any element AK, any left coset AK की cardinality is equal to BK की cardinality is equal to cardinality of subgroup K. And since we will use the result of a set theory, since these all are distinct, then cardinality of G is equal to cardinality of I from 1 to R A I K is equal to summation I from 1 to R A I K. We can write as, for example, cardinality of A union B is equal to cardinality of A plus cardinality of B minus cardinality of A intersection B. Since all these AIK are left cosets are distinct, that means AIK intersection AJK is equal to 5. That is why we can write as cardinality of AIK is plus, and this minus thing will be 0. One more result, we need to know that a left coset AK and BK are either disjoint or equal. That means this is AK and this is BK. These are disjoint, or if there exists a common element between AK and BK different left cosets, then this implies that these will be the same. AK is equal to BK. So there can't be any common element in disjoint or distinct left cosets. So this can be written. Now use this result that left coset with respect to A की cardinality is equal to left coset with respect to B की cardinality. That means this is equal to R into K की cardinality. So right here, order of G is equal to R into order of K. So R is equal to Z divided by order of K. What is R? In the beginning, we have taken R as number of distinct left or right coset of K in G. That means index of K in G is equal to R. So index of K in G is equal to order of G divided by order of. Similarly, index of K in H is equal to order of H divided by order of K, and index of H in Z is equal to order of G divided by order of H. Now, what the question asks is this that multiply index of H in Z into index of K in H. So index of H in Z into index of K in H is equal to order of G divided by order of H into order of H divided by order of K. So this H, order of H will be cancelled out, is equal to order of G divided by order of K, which is the index of K in G. This is what we needed to prove. That's it. Now we used three results that Z can be written as a union of distinct left cosets. Second is this, that cardinality of different distinct left cosets is equal to order of K. And third result is that either these are distinct or are equal. So first let us prove that R1, that Z can be written as union of distinct left cosets of any subgroup H. So we know that it means G can be decomposed or partitioned into distinct left cosets. So for that we need to define a equivalence relation. Let us define a relation. A is related to B if and only if A inverse B belongs to H. So first of all, this we need to prove that this is a reflexive. Since identity belongs to H, that means A inverse A belongs to H. That implies A is related to A. Second, we need to prove that this is symmetric relation. So A is related to B. That implies A inverse B belongs to H. And since H is a subgroup, that means A inverse B ka inverse belongs to H. This implies B inverse A belongs to H. And this implies by the definition B is related to A or B are A. Third, we need to prove that this is transitive relation. This implies symmetric relation. For transitive, let A is related to B and B is related to C. This implies that A inverse B belongs to H, and this means B inverse C belongs to H. Multiply both of these, then A inverse B into B inverse C. belongs to H, since by closure property H is a subgroup, so the product of both these will belong to H. That means P will be cancelled out. A inverse C belongs to H. This means A is related to C. We assume that A is related to B, B is related to C, then A is related to C. This means it is transitive. Hence, this relation defined by A is related to B if and only if A inverse B belongs to H is a equivalence relation. And we know that equivalence relation means this relation, the equivalence classes will partition the whole set. So Z is equal to union of equivalence classes I from 1 to R. Then now we need to prove that this equivalence class AI is equal to left coset of H. To prove this, let X belongs to AI. That means X is related to A. This means X inverse A belongs to H. This means X inverse A का whole inverse belongs to H. This means A inverse X belongs to H. Multiply both sides by A. Operate both sides by A inverse X belongs to AH. A and A inverse will be cancelled out. X belongs to AH. So we assume that X belongs to equivalence class of AI. Here we can write AI all the way. And finally, we have proved that X belongs to AIH. This means equivalence class AI is a subset of AI. Similarly, we can prove the other way around. So this means union I from 1 to R equivalence class AI is equal to AIH. This we needed to prove that Z can be written as union of left cosets. Now second result, we used another result. Result 2 is that cardinality of AK is equal to cardinality of BK is equal to K. This we can prove by defining a function f from AK to BK. Now this is defined as AK1 is equal to BK2, where K1 and K2 belongs to capital K, that is a subgroup. This is a 1-1 onto function. Easily it can be proved. This that implies cardinality of AK is equal to cardinality of BK. And when this A or B is equal to identity, then it will be equal to EK, that is K. This we have proven. We have proven second result, and third result is that either they are equal or they are disjoint. This we already have proved that this is equal to equivalence class of A, and equivalence classes are either disjoint or they are equal. So this is it. Actually, this question, people said that this is equal to order of G divided by order of K, and this is equal to order of G divided by order of H multiplied by order of H divided by order of K. So cancelled out. In 3 lines, we have solved this question. But this will not fetch you 10 marks because so many results we have used. We need to prove that we need to prove that this is equal to this. That is the main thing in this question. To prove this, we used this partition thing and these results to prove this. That is why it is a long question. Thank you guys. You can join our Telegram group to ask your doubts.